manipulate this signal, you alter the function of whatever that neuron that you try to manipulate. You learn that in a minute later. All right. We talk about this over and over again. With all the sodium coming in, the potassium coming out, okay? Eventually, if there is no intervention, your ion concentration will be equalized on both sides. And these pumps are constantly working. The sodium coming in will pump right back out. The potassium that, is it wrong? The potassium that coming out, that will be pumped right back in. So that you're ready to go to the next one. And you know sometimes you talk a lot in terms of the neuron. We also learned that action potential not only can be generated, action potential can also propagate. In other words, travel. They also travel. And how can that be? Look at that picture right here. What they show you is this. Those are the voltage-gated potassium sodium channel. You see that? So whatever that causes this channel open, the action potential generated right there, indicated by that line, right? Well, it turns out that if this channel is a voltage-gated channel, the other channel are also voltage-gated channel. So if the voltage change right here, it will cause the other channel in turn will open, almost like a domino effect. You remember the right? If one domino fall down, it causes the other one fall down. Therefore, when an action potential generates right here, it will cause the other sodium voltage channel open. Therefore, the signal can spread in both directions. Hypothetically. Do you guys see that? Okay, and that's how the action potential able to propagate. The question we learned is, in action potential, in the axon, it only travels one direction. But you learn right here, it has potential go either way, right? So why is that? In the neuron, the action potential only go one direction, which is from cell body to the axon terminal. Why is that? If you recall, the structure named axon hillock. You know that structure? Right? Axon hillock is where here's the cell body, and that's where the axon came out. And remember, I told you guys that when the neuron decided to generate an action potential, that's where it started right there. Why is that? When the action potential operate or generate at axon hillock, okay, right here, it always travels down this right here. It does not go back to the cell body. You know that action potential nowhere to be found, right? And here we learn, pretty simple, because axon have many voltage-gated sodium channels, where in the cell body you don't have that many, and therefore the signal do want to go either way. They go this way or that way, right? But there's no sodium channels to support that signal, so the only way they can go is down the axon. Is that cool? Look at that, it's cute. You should have a t-shirt. Okay? Okay, this slide right here explains something that I mentioned before. Remember the term all or none? That means that when you see an action potential, you will see an action potential with 1 millivolt. Not 70, not 120. All or none. Either you send it or you don't. And the reason why we see that, because right here. Let me see right here. Because when the membrane potential reaches minus 55, the channel open, and that's the only way to go. Right? You open the channel, you will see action potential. You don't open it, you don't see action potential. And that's what I mean by threshold right there, 55. The question you didn't ask is, okay, I know why. That's why the channel open. What make the membrane potential go from minus 70 to minus 55 so it can open the channel? Well, that's a whole long story later. This is what I'm talking about. Because all action potential, either all or none, right? They look the same. So how do we ever communicate by different modality that a human brain can communicate? That's what I mean right there. It's the coding, the frequency, how to communicate.
Dr. Vu.
Yes, ma'am.
Can you pass around the attendance?
Are you concerned about the quizzes, Lauren?
Mm-hmm.
Fine. She take over, Adil. She take over your role. Yes. All right. How about this? I don't think I want to go to this detail without go further, and I don't have time to go any further. Go ahead and just gently and regrettable that put the term omit in it. You are not responsible until for this slide right now. And we move on. me ask you guys this. Have we talked about this? The speed that an action potential travels in an axon, the velocity, it determined by two factors that I have talked about. Remember we talked about nerve fiber, we have three types, A, B, and C? Remember that? So what two factors they rely on? First, the amount of myelination, right? The more myelination an axon has, the faster action potential travel. What's the second criterion? The diameter of the axon. The bigger the diameter, the faster the action potential travel. That's how we have classified A, B, and C. Another thing we learned is when I talk about the action potential travel, we always imagine, oh, here's a channel, it travels nicely in the long linear pathway. That's not the case. The action potential actually jumps like a frog. Okay? The action potential actually jumps from one node of Rothier to the next. Why is that? Let's look at the mechanism. That is a myelin sheet, and you see that at the node Rothier, you don't have much myelin sheet. When I told you guys that the action potential, oh, by the way, if this cell right here generates an action potential, right there, the action potential is, what's the amplitude? Okay? If I follow down there all the way, wherever they go, weight goes somewhere, you measure the action potential again. By logic, the signal should diminish somewhat, right? It's still, it's 100 millivolts. Doesn't change. When I said that, I just lied a little bit. Okay? It does change, but it changes so fast you don't see them. Why is that? Right here. When the action potential travel, and you can see that the area underneath the myelin sheet right there are not many ion channels underneath them. So between one node Rothier to the next, the signal actually slightly diminished. Okay? But when that signal arrives at the next node Rothier, where they have a high concentration of sodium and potassium ion, boom, they rejuvenate, boom, they're back to 100 again. Because it occurs so fast, you don't see the difference. Okay? So you see signals, instead of just travel like this, it does this. And by doing so, they also travel faster as well. And sometimes people cannot grasp that. Compare, if the kangaroo can run, compared with the kangaroo that jump, which one can go faster? The jumping is faster. However, it becomes more energy. And that's what they call the saltatory conduction. What do it mean? The signal do not travel in the continuous linear pathway. It actually jumps from one node of Rothier to the next. Another thing we mentioned about the myelin sheet, okay? There is an autoimmune disease. Autoimmune disease means that your immune system becomes nut. Instead of killing the invader, protecting you, now it attacks your own body. And in this case, guess what specific tissue that your immune system are attacking? The myelin sheet. A myelin sheet. And that is a famous disease we call MS, multiple sclerosis. Okay, where you go to the 7-Eleven little bucket where they say put a dime in there or put it in there, don't have to research. Okay, because we still study, we don't know the cause of that yet. You say, what's the big deal? Right? How about this? If I have about 10 live electrical wire on my hand, they're all live, right? I can hold them. Why? Because they're all protected by the rubber around them. You don't care. I can hold 10 of them, 1,000 of them, doesn't matter. But what happens if one of them peel off? The rubber came off. Okay? You mean that now I can hold them? Now that electrical signal can be conducted through my body. Does that make sense? And that's what happens when a myelin sheet being attacked by immune system. They losing the protect layer. Now the signal is supposed to travel along the axon from cell body to axon terminal. It may come and go somewhere else. Okay? It may shock the other neuron, whatever that is. And that is multiple sclerosis. The bad news is we know more than we did before, but we don't know exactly all the mechanisms that. And one thing that happens is the shunting. The signal now no longer go where it's supposed to go. It's spread out everywhere. And the severity depends on where it occurs. Even though it has potential to occur throughout the body, but the most common system that affects the most is the visual disturbance. Okay? They distort your visual. Because you learn later that what nerve go through the optic foramen of the sphenoid bone? Optic nerve. And that like a cable that carry the image from the eyeball into the brain. Okay? Well, no, that's different. But that cable right there, if the signal now spread throughout, you can't see that image because the signal now distorted. What else? Loss of the muscle. That makes sense. Because when the motor neuron sends action potential, that action potential has to travel the entire length of the axon and arrive at the NMJ. Well, in this case, they go somewhere else. Therefore, the signal not as strong. They won't open enough the neurotransmitter to release. The muscle become really weak. Another thing we also find out common in the MS is individuals become urinary incontinent. In other words, they cannot control their bladder. They cannot control their bladder. That reminds me of something that when I first entered the United States, I learned a lot of things in a funny way. Okay? Because at that time we don't have CVS. At that time we had Echo. I remember that. I go to Echo and search for something, and I go to the aisle, and I see the whole package they call dependent. You know what it is? Right? Dependent.